All right, so welcome to Mini 2 of 10600 Math Background for Machine Learning. For those of you who have been in Mini 1, a lot of this is going to be old hat, but for those of you who are new, you can see we're running this course entirely online. That means that all of the assignments will be completed online, all of the lectures are streamed like this one, and we have online office hours available as well. So the way that works is if you want to ask questions, you can just message the TAs. So the Hangouts contact information for the TAs is on Piazza, or you can directly ask questions on Piazza. And the TAs will be monitoring that. I obviously won't because I'll be paying attention to the slides or the whiteboard. But the TAs can message me if they can either answer questions or message me if there are common questions. And I'll cover those in the lecture stream. I guess the other thing for new people is that we're going to spend a decent portion of our class time actually working on problems. And so I'll hand out problem sets, and those will typically be due midnight the same day to give you a little bit of time just in case you don't see the answer immediately during class. But we're available during class to answer questions about them. And as with the lecture topics, any common questions I'll try and address in the lecture scheme. We have a whole bunch of information on Piazza. If you're interested in course policies like collaboration or grading, that's all on Piazza. If you're interested in the syllabus, that's on Piazza as well. So go sign up for Piazza, log in, and see what we got to offer. All right, so let's get started. So the first topic for this mini is going to be modeling. And we're going to start modeling by talking a little bit about information theory and entropy, which is going to be helpful for us as we go on. So let's go and switch to the slides. So so here we go. So we're going to start with the idea of information. And information is it's one of a bunch of equivalent ways to look at things. And so the nice thing about it is that it has a very concrete interpretation in terms of bits, messages that people send back and forth between each other. And so it's often a good way to get intuition that's maybe hidden a little bit in other ways of thinking about the problem. So let's start by talking a little bit about information. So suppose we have a random variable. We'll call it x, and it's a discrete random variable taking values in 1 through k. And suppose that we have two people, Alice and Bob, because it's always Alice and Bob for some reason. Alice and Bob both know the distribution of x, p of x, but only Alice knows the actual value of x. And so Alice has more information than Bob, but let's try and quantify how much more information Alice has. And so the way we do that is we're going to start by, ask Alice to tell Bob the value of x. So they're going to have some communication channel where Alice can send bits along the communication channel, and if she can use b bits and Bob will then know the value of x, then Alice has at most b bits more information than Bob does. Alice could have less than that. She could have used an inefficient way of encoding the information, but at least if she can do it with b bits, then she's good. She has at most b bits more information than Bob does. And so how are we going to do that? Well, we'll agree on a code. A code is basically just an assignment of a code word, a string of bits, to every possible value of x. So Alice and Bob agree on the code ahead of time, and then when Alice sees x, she transmits the corresponding code word to Bob, and everything's good. So for example, if you've got 4 possible values, you could have the code words be all the possible 2-bit strings, 00, 01, 10, 11, and that means that Alice can inform Bob using at most 2 bits. She might be able to do better, but at the very least she can do it using 2 bits. So that's interesting, right? So under what situations could she use fewer than 2 bits? So let's look at these two distributions here. Here's a uniform distribution, and here's a distribution that's not uniform, right? It's got much more weight on 1 than it does on 3 or 4. By the way, again, for the new people, all of these lecture notes that I'm going through during class, you can find them on Piazza. They're linked from the syllabus page. The syllabus page is your friend. It has all of the information about lecture notes, homework assignments, what topics we're going to cover. So please try and check the syllabus regularly, and we'll try and point you to the syllabus when anything particularly interesting like a homework assignment goes up. All right, so we got these two distributions over x. One is uniform, the other is not. In the uniform distribution, it seems like the simple code of just the 4 possible 2-bit strings is the best we can do. But maybe we can do better if we're in the situation of the non-uniform distribution. So in particular, suppose we pick this code right here, right? So Alice assigns the bit string 0 to the first outcome, 1, 0, 1, 1, 0, 1, 1, 1, and 1, 1, 1 is the last outcome. And the interesting thing about this code is that there's a very short bit string, 0, for the most probable outcome, and we have longer bit strings for the less probable outcomes. Now, it's not obvious ahead of time that this is going to help, right? Because sometimes we're using 3 bits instead of 2, and sometimes we're using 1 bit instead of 2. But if we work it out, half of the time we're sending 1 bit, quarter of the time we're sending 2 bits, an eighth of the time we're sending this 3-bit string, and an eighth of the time we're sending this 3-bit string. And if you add that up, on average, Alice is only using 1 3/4 bits instead of 2 bits, so she's saving. Now, not every set, given that the strings are different lengths, not every set of strings is okay. And we're going to enforce a property that's called the prefix property, which is that no code word can be a prefix of any other code word. So 0 is a code word, and none of the other code words start with 0. 1, 0 is a code word, and none of the other code words start with 1, 0. And what that means is that if Bob sees 1 followed by 0 coming over the line from Alice, then he knows he's done. Right? He doesn't have to wait for any more bits to come over. He knows he's at the end of the message. And we're going to enforce that because you can imagine that this communications channel, it's in use for a whole bunch of messages between Alice and Bob. And Bob has to know when each one of the messages is over in order to be able to start looking at the next one. All right, so we used 1 3/4 bits instead of 2 bits by picking our code. Could we have done even better? Turns out the answer is no. It turns out that we can put a lower bound on how long the code is that we need. And that lower bound is through a quantity called the entropy. So the entropy is going to be, you can think of it as the expected code length, right? So the sum, suppose that we assign minus the log base 2 of the probability. Suppose we assign that many bits to each one of the messages. Right? So if we go back up here, right, we had a 1/8 probability outcome here, and minus the log of 1/8 is 3, right, 3 bits, and we assigned a 3-bit message to that outcome. So if we do that always, then on average we're going to spend sum over all outcomes of the probability of that outcome times the length of the message if we have that outcome, right? And so the entropy you can think of as how many bits am I going to have to spend if I'm able to come up with a code that assigns this many bits to each outcome. And so, for example, with our distribution that put a 1-bit message on the half probability outcome, 2-bit message on the quarter, 3-bit on each of the 1/8, we get that the entropy is 1.75 bits. And so that turns out to be a lower bound, although we're not going to prove it here. So it turns out that this lower bound is tight. You can always achieve it. And there's a very cute algorithm called arithmetic coding, which again, we're not going to cover here. Just it's enough here to know that it exists. But there's a cute algorithm called arithmetic coding that gives you a code that on average uses log 2 of the probability bits for sending an outcome that has that probability. And if that's not an integer number of bits, then that sounds kind of weird, right? But we're only going to use it on average. So we imagine that we have a long string of messages. Alice keeps finding out different realizations of x and keeps having to tell Bob about these. And on average, over all of those repetitions, she's going to use log p bits for an outcome that has probability p, minus log p bits for an outcome that has probability p. So this here looks like a typo. That should be minus log p, because the probabilities are always going to be less than 1, meaning the logs are negative. I'll try and remember to fix that after class. All right, so that means we're going to use entropy to measure information, right? So we're going to say that supposing that Alice uses an optimal code, how many bits is she going to need to transmit the information to Bob? That is the entropy of the random variable that she's trying to transmit. All right. So if we check out the corner cases of entropy, that gives us something that makes sense. The highest possible entropy distribution is the uniform distribution, and its entropy is going to be the log of the number of outcomes that there are. So if there are 16 outcomes, it's going to be entropy 4. And then the lowest entropy distributions are going to have entropy 0. They're going to be the one where Bob already knows the answer, and so Alice doesn't need to transmit a message at all. So far we've been imagining binary, but you don't have to use a binary alphabet. You could use an alphabet with 3 or 7 or 142 symbols in it. And you can measure entropy in that alphabet as well. You just measure how many symbols you expect to need to transmit. And that number of symbols, it's just going to be you replace 2 by whatever the number of symbols is in your alphabet. So log base a of p instead of log base 2 of p. And if you have 16 symbols available to you, each one of those symbols is going to be 4 bits, and so you're just going to have a conversion factor of 4. You're going to need a factor of 4 fewer symbols than you would need bits. We can even actually use non-integer bases, and there's not really an interpretation of that, except that you can convert to an integer base and use an alphabet of that size. And the conversion will work the way that you expect it to. So if you measure information base E, it's called nats instead of bits. All right, so that was one random variable. What if we have 2 random variables? Well, that's actually the same as the case that we had before, right? So if we had a random variable x and a random variable y, we could make a vector-valued random variable z, which is just x concatenated with y. And we could ask what was the entropy of z. And you get, well, this is the formula for the entropy of z. And if you break that down into x and y, it's just a double sum over x and y of p of xy log 2 p of xy. And so this entropy of this joint distribution is called the joint entropy. Essentially the same thing as the ordinary entropy. But now we can ask another interesting question. What happens if Alice tells Bob about y, but hasn't told Alice about x yet, right? So Alice started out by having the entropy of x and y together, the joint entropy. She started out having that much more information than Bob did. And she gave Bob information worth h of y. So that's how much less information she now has over Bob, right? And so we're going to give a name to that. We're going to call that the conditional entropy, h of x given y. So h of x given y is going to be just h of xy minus h of y. And if you work it out using the definitions of conditional probability, you can get down to this expression here. Sum over x and y of the joint probability of x and y times the log of the conditional probability of x given y. And it looks like I have skipped the minus sign here as well. I apologize for that. It's very, very easy to leave out the minus sign, and you'll see in the end you'll get a negative answer, and so you can detect that mistake. All right, so this is the This is the conditional entropy. You can think of this as how much information in X is unique to X and not provided if you find out Y, right? And this is an in expectation. This is before knowing the values of either X and Y. How much extra information do you expect to be in X compared to what's in Y? Now, if you already know Y, you can ask what is the extra amount of information in X given the event that big Y equals little y, right? That the random variable equals some outcome. And that's just going to be the entropy of the conditional distribution of X given that particular outcome. And so you can actually write the conditional entropy in terms of this. You just take the expectation of this with respect to the outcome of Y, right? So this is yet another expression for the conditional entropy. All right. So if you're going to work with the joint and conditional entropy, there's a very nice identity called the chain rule. Unfortunately, it turns out there are a lot of identities called the chain rule. There's a chain rule for probabilities and a chain rule for derivatives, and this is the chain rule for entropies. So don't try and confuse them and take derivatives of entropies when unless you actually want the derivative of an entropy. And the chain rule for entropy is basically the joint entropy is the entropy of the first variable plus the entropy of the second given the first, plus the entropy of the third given the first two, and so forth all the way up to the entropy of the last one given all of the previous ones. And if you have the entropy of each of the individual variables separately, in other words, if you transmit X without reference to Y, and then you transmit Y without reference to X, maybe you transmit them to two different people, you're always going to use at least as many bits as if you were able to transmit them together, right? And there's going to be equality if and only if those two variables are independent, right? You're always going to be able to buy something to be able to use shorter messages if there's some statistical dependence between these two when you transmit them jointly. All right, so next is relative entropy. So let's go back to just X, right? Forget about Y, suppose we just have X anymore. What if Alice and Bob have the distribution of X wrong, right? So what if they think the distribution is Q when the true distribution is actually P? So in that case, they're going to pick a code that's based on Q, and it's going to use minus log 2 of Q bits to transmit each value. And so the expected cost is the sum over X of minus P of X log Q of X bits, right? And that cost is always going to be higher than the cost of an optimal code because it's not an optimal code. And the extra cost, the difference between this cost and the cost of the optimal code, is called the relative entropy, or the KL, or the Kullback-Leibler divergence, right? And so here's an expression for it, combining those above expressions. And just like before, we can measure it in bits or nats or whatever other base we like. The most common thing is probably to measure it in nats, in other words, to use the natural logarithm. So relative entropy generalizes ordinary entropy in the following sense. If Q, the distribution that you actually use, is uniform, then KL is a constant away from the entropy of P. And so KL lets you compare pairs of distributions to see essentially how much more information is in one of them than the other, right? Or how much information is in one, supposing that the true distribution were the other. A few properties of relative entropy. It is asymmetric. The KL of PQ is not equal to the KL of QP in general. If you look at this expression here, right, you have a P log P and a P log Q. If P is large where Q is small, this minus log Q is going to be huge, and you're not going to be, if P is, an ordinary, 0.1 or something like that, you're not going to be, you can make log 2, minus log 2 of Q be arbitrarily large by making q close to 0. And so you can make the KL divergence be really large by making q small where p is not small. Right? And the KL divergence achieves a minimum when p equals q, right? Because then this expression is obviously 0. Log p and log q are the same, and they cancel out. And you can think of this as saying, all right, suppose that I code using q and assign a very long code word to an event that is actually probable, even though q says it's really improbable. Then I'm going to be paying a lot for my code. All right, so you can do all of this. I've been talking about discrete variables so far. You can do all of this for continuous random variables as well. And basically what you do is you replace sums by integrals. Now, in some sense, that takes no thought at all. You just replace the sums by integrals and everything happens. But in some sense, it takes a lot of thought, because as soon as you open up continuous random variables, you're opening up a big can of worms. In particular, coordinate systems make a really big difference. If you do a change of coordinates, the entropy could actually change, and so you have to think about what is the right coordinate system to be measuring in. And also non-smooth probability distributions. You have to make sure that the integrals actually converge, right? Whereas the sum for a discrete probability distribution, it's always no problem. The other thing that's a little weird when you think about entropy for continuous random variables is that suppose the communication metaphor breaks down. Suppose that Alice has to tell Bob the value of a continuous random variable, a sample from a Gaussian distribution. Well, that's going to take Alice a really, really long time, because there's infinitely many bits in the description of that sample. And so if you think about the discrete entropy of that continuous random variable, it really should be infinite. So what does the entropy actually mean? The best interpretation that I know of is that the entropy of a continuous random variable, it only makes sense in terms of differences. How many more bits do you need to transmit x than you do to transmit y, where x and y are two continuous random variables. And in particular, we set the scale so that if y is we set the scale so that the comparison variable y is uniform on the interval 0, 1. So that's defined, that random variable uniform on the interval 0, 1 is defined to have 0 entropy. And every other random variable is defined, its entropy is defined by comparison to that touchstone, to that comparison random variable. You could need more bits to transmit x than the uniform, in which case you'd have positive entropy, or you could need fewer bits, in which case you'd have negative entropy, right? And that brings up another point, which is that the continuous entropy can be negative, which is sort of a weird thing as well, right? A discrete entropy can't be negative because you can't have information that's worth a negative number of bits. But again, because continuous entropy is only by comparison to another continuous random variable, you're just asking how many more or fewer bits you would need. And what do I mean by more or fewer bits? Well, okay, suppose that Alex is going to transmit x as an IEEE double, right? And y also as an IEEE double. How many more or fewer bits does Alice need to transmit x than to transmit y, right? And you can discretize x and y at any resolution, but as long as you discretize them at the same resolution, it's fair. And then to get the continuous entropy, you take the limit as that discretization approaches infinitely many bits. So the limit of the difference in the number of bits as the discretization gets finer and finer. All right. So continuous entropy is a little bit weird compared to discrete entropy, but it does still have an interpretation in terms of communication. You just need to understand the two things. One is that it's only a comparison. How many more bits do you need for one random variable than the other? And the other is that you have to involve a discretization somehow if you want to transmit a finite number of bits. All right. And maybe this set of equations is worth going through. So let's suppose that we have some continuous variable x on the interval 0, 1, and we compare it to are uniform on 0, 1 distribution. So let's split 0, 1 into k equal bins. And the probability that x falls into a bin of width 1 over k, ending at I over k, that's about p of x equals I over k, right? So the continuous probability density of x at I over k times the width of the bin. And the entropy of a uniform distribution on k bins is log k. In whatever base we're using. Here I'm using the natural log. So the difference in entropies is the sum, right? The entropy of the number of bits for x is the sum of 1 over k p of I over k times log of 1 over k p of I over k with a negative sign. And with y, it's log k. We can bring that log k over and cancel, right, this 1 over k, right? Because minus log k is the same, right? This is minus log 1 over k and minus log k. They cancel each other. And we're bringing it inside a sum over probabilities, which sums to 1, so it's okay. So now you have limit as k goes to infinity of 1 over k times this expression. This expression is p log p evaluated at a discrete grid of k points, averaged, right? And the limit of that as k goes to infinity is defined to be, right? That's the Riemann definition of an integral. So it's defined to be equal to this integral, which is the continuous entropy. All right. So I've got a question. Why is the conditional information result on the natural log? Did I... go back up here to the... right, I didn't specify a unit up here. So there's, anytime you measure information, you can measure it in any base you like. I happened to do it in natural log here. All of this would go through just fine if it were the log base 2. It's just that the unit of entropy would become bits instead of nats if I used log base 2. Right? So all of the identities about entropy, it doesn't matter which base you use for your log, as long as you remember that the result comes out in a unit that depends on what that base is. So maybe if you prefer, you can actually just go through and replace all of the natural logs by log base 2, and all of this is true still. All right, so let's think about this in the context of machine learning, right? So in machine learning, it comes up pretty often that we've got some parameter we want to estimate, call that theta, and we start off with a distribution p of theta, and that distribution has some entropy h of theta. And over time, so we're in the position of Bob here, right? We know the distribution of theta, but we don't know theta itself. And over time, nature, in the role of Alice, sends us some information over a communication channel. And that information is the samples that we receive in order to estimate theta. And so we have samples x1, x2, and so forth that give us information about theta. And I'm not going to talk about exactly how that information comes in, but let's just assume we start off with a prior over theta, and every time we get in a new observation, we update it to get p of theta given x1, p of theta given x1 and x2, and so forth. And our entropy is going to evolve in parallel to be the entropy of that distribution. And so this entropy measures how much information we have about theta. At the beginning, we have high entropy, meaning not very much information. And over time, our entropy is going to tend to decrease, at least if we're getting relevant samples, relevant information x. And so our information is going to increase and our entropy is going to decrease. We're going to get more information. That decrease, in expectation, it's going to be monotone, but in any particular run of our machine learning algorithm, it can be non-monotone. We can get a surprising observation, and that will cause us to reset our distribution a little bit and have higher entropy. I've got a question about whether entropy over a continuous random variable is used in machine learning. Definitely yes. We're actually going to, in the next set of lecture notes, see one example where we look at maximum entropy distributions. Actually, this section 11 of this set of lecture notes, is a place where we're looking at continuous entropy because theta, the parameter, is typically going to be continuous, and so we're going to be measuring the entropy of a continuous distribution. All right, so what I would like to do now is have you guys do a few exercises that are related to entropy. And so give me just a second and I will post the exercises on Piazza so that everybody can see them. All right, so I've gone ahead and posted these exercises. And you guys can, oh, it looks like it didn't come out as an actual link. Let me make that a link so that it's easier for you guys to click on. There we go. So these exercises are going to be about entropy. And as usual, you're going to have until midnight tonight to do them. And you can have a look over the exercises. Hopefully the lecture notes that we've just gone through should give you enough information to be able to do all of the exercises. But please look over them, start to do them. We'll wait a few minutes before we start any additional lecture content. And so please ask us questions and we'll go ahead and try and answer them before we move on. Hey, all, there's a question about whether the questions about entropy are measured in bits or nats. Um, the Whenever we ask you to give an entropy, we should tell you specifically whether we mean bits or nats. And I tried to do that in all the questions, but I might have forgotten to do that in one of the questions. So just, if you can't tell from the question before answering it, just shoot us a note and we will try and clarify. Hey, also, a clever person figured out that I asked the wrong question for question 2. So if you were worried about question 2, don't worry about it. We won't count that question in the grade. I've updated the question so that it has hopefully now a correct answer. So if you want to reload the page, after of course submitting any answers that you've entered in, if you want to reload the page, you'll get the new version of the question. I apologize for that, and like I said, we're going to remove question 2 from the grading for this assignment. So before we get too far into the assignment, I'd also like to go through an example that's relevant to question 7 of the assignment. So let's take a look at that example. So suppose that sorry. There we go. Suppose that we have some data that looks like this. We have x and y, and x is, let's say, a number, 1, 2, 3, and so forth, and y is either 0 or 1. So let's say when x is 1, y is 0. When x is 2, y is 1, 0. And we have, let's say, 7 samples that look, sorry, we're going to call them 0, 1, 1, 1. Okay? So this is some data. And let's suppose that I would like to learn a classifier of the form, is x bigger than or equal to theta, right? And I would like to say that if yes, then y equals 1, and if no, I predict y equals 0, right? And these are both predictions. Okay, so which value of the threshold should I pick, right? Well, so from this data, I can't tell anything about the difference between 2.6 and 2.7, right? So I can only tell if the threshold is smaller than 1, if it's between 1 and 2, between 2 and 3, and so forth. So I might as well take the threshold to be a half integer, 0.5, 1.5, 2.5, and so forth. And then what I'm asking is there's going to be a variable t, which is equal to 1 if x is greater than or equal to theta, and 0 if x is less than theta. And I'm asking for what is the entropy of y if I know t, right? So that's how much information do I expect to need to get the value of y if I know t. And I would like that to be as small as possible, right? I would like to have as little additional information required as I can arrange. And so asking where I should choose theta is the same as asking a question about the conditional information, right? So in particular, the conditional information tells us exactly how many more bits should I expect to need to tell you y if I already know t. And so the best t is going to be the one that leaves the fewest bits of information. And we can go and you can write a simple program in the language of your choice, MATLAB, NumPy, whatever, that will compute for each division you could put your threshold here, you could put it here, and so forth. For each one of those divisions, what is that conditional entropy? And you can use the formula for conditional entropy to evaluate it. And if you do that, for this example, it turns out that the optimal value is right here, right? So theta equals 4.5 is optimal. And you can sort of see that because if we divide here, right, there's going to be 3 out of 4 on the left are zeros, so we have a fairly low entropy distribution here, and 3 out of 3 on the right are going to be 1s, and so we have a really low entropy distribution over there. And so, if we were to move over by 1, right, we'd include a 0 in with the 1s, and that would get worse, and we'd strip off one of the zeros, and so we'd make this higher entropy as well, right? So you can see that it's sort of locally optimal. And if we want to calculate what that number actually is, right, so in this particular case, h of y given t, it's going to be the probability that we wind up on the left, which is 4/7, plus times something, plus the probability that we wind up on the right times 3, which is 3/7 times something else. The something else over here is going to be the entropy of this distribution, which is 0. And the something else over here is going to be the entropy of this distribution, which is the entropy of the distribution 1/4, 3/4. Right? And if we work that out, we get some number, and it will turn out that that number is lower for this split than for any other. All right, we're getting a question as well about how to calculate bit rate. So that's actually entirely what that question is supposed to have you guys figuring out. So I don't think I can answer it directly, right? The question is about bit rate versus symbol rate. So the question says to consider 2 alphabets, one with 16 symbols and one with 64 symbols, and suppose that the symbol rate is the same, right? So we have 2 codes at the same symbol rate, and one has alphabet size 16 and the other has alphabet size 64. So you have to ask yourself, how many bits per symbol can the first one transmit, and how many bits per symbol can the second one transmit, and what's the ratio between those two things? That's maybe the best extra information I can give for that question. All right, I'm going to go back and let you guys work for a little while longer before we move on. Hey all, I just wanted to say there's about 15 minutes left in the class period. So I've been watching the statistics for attempts on the problems. Very few people have had a chance to attempt problems 6 or 7 yet, and those are the hardest two problems. So my thought is let's spend the last bit of the class period. You guys can take a look at those two problems and ask any questions. Make sure you know how you think you're going to solve them and ask any questions that you can think of. And I will hold off on starting the next set of lecture notes until Wednesday's class. So please feel free to continue asking us questions. And I have office hours starting immediately after class. So the way that works is you can just send me a message on Hangouts if you'd rather do it online. You're also welcome to stop by my office, but since we're a completely online class, we're offering online office hours as well. Somebody asked me to explain again how to calculate the optimal threshold in this problem here. And so for this problem, what we can do is try each value of theta one after the other, right? And you should, maybe write yourself a little computer program to help you evaluate a specific value of theta. And the way that you evaluate that particular value of theta is by calculating the conditional entropy of y, given whether you're above or below the threshold, right? And so I showed how to calculate that for one particular value of the threshold, right? So the probability that you're over here times the entropy over here, plus the probability that you're over here times the entropy given that you find yourself over there. And so it's not like, for example, you can't take a derivative and set to 0 because it's a discrete choice of theta. All that you can do is just try all of the possible values of theta, and you can do that in a for loop, or you can just do it manually. All right, so I'm going to end the lecture stream now. Looks like some people have at least gotten a chance to start on problem 6 or 7. As always, you guys have until midnight to finish these exercises. And my office hours start now. I'll be here at least until 3:30, available over Hangouts. So thanks a lot, and I'll talk to you guys on Wednesday.